First, I'd like to thank John for inviting me to the University of Arkansas for all of their hospitality, and Chris Gray for his marvelous talks, and the other speakers as well. So today I'm going to talk about something that is very distant from anything that's been mentioned so far. Well, people have mentioned complex numbers, but I'm going to talk about complex manifolds and complex structures. And since, several complex variables is a subject that either you don't work in it or you're an expert. So either you've never heard of it or you're an expert. So I think I'm going to start here at the beginning, and I'll work my way up to actually discussing what is a very kind of esoteric and technical question in this field. But nonetheless, I spent a lot of time working on it. So you start out with an even-dimensional manifold, and how do you define what you mean by a complex structure? Well, we'll start out first of all by picking a section of the endomorphism bundle of the tangent bundle. So that's very geometric, with the property that it squares minus the identity. So this is a real endomorphism, but since it squares minus the identity, we know that its eigenvalues are plus and minus I, and so we're only going to find eigenspaces if we complexify the vector space. So this is what we do. We complexify the tangent bundle, and then there are two eigenspaces. We let T01 be the minus I bundle of eigenspaces, and its conjugate is the bundle of plus I eigenspaces. So this is what is called an almost complex structure. It's just something algebraic. There's nothing analytic about this construction. So then if I want a real genuine complex structure, I need to impose an integrability condition. And that condition is just this formal integrability, that if Z and W are two sections of my bundle, then the bracket should also be a section of my bundle. Okay, now it's not an obvious statement that this is the same thing as what we ordinarily understand as a complex manifold, but it's still true. Once you have just this structure, you have this 0,1 subbundle. You can define the d-bar operator, and the d-bar operator is just the exterior derivative restricted to this 0,1 subspace. And we say a function is holomorphic if d-bar f is 0. So it's not obvious there are any holomorphic functions, but there are, because of course that's an overdetermined system of equations. It's n equations or n complex equations for one complex value function. But in fact, the integrability condition implies that there exist local coordinates, local holomorphic coordinates, which are solutions of this equation. And holomorphic coordinates, this d-bar operator takes a very simple form, which we've written here. And the complex vector fields are just written there at the bottom. So, starting out with some geometric object, you end up with some very familiar analytic object. The transition from the top of the page to the bottom of the page is the Newlander-Nirenberg theorem. So, but it was proved in 1957. It was a very important result, and a hard result. Okay, so but I'm interested not in complex manifolds so much as real hypersurfaces in complex manifolds. So real hypersurfaces and complex manifolds have on them a structure, which is called a CR structure, which is sort of the odd-dimensional analog of a complex structure. Now, notice, it only exists when the dimension of X, the manifold that I'm working on, is at least 2, its complex dimension. So this is why most people have never heard of these, because in functions of one complex variable, there is no such thing as a CR structure. So you have to have at least 2 complex variables for the structure to exist. So this is what you do. You have a hypersurface sitting in your ambient space. System here. So you have a complex, I have a complex manifold. I have a hypersurface. This would work. Line. You don't have to write upside down X. And then we say a vector is in this subbundle T10B, which is the subbundle of the complexified tangent space of this hypersurface, if, first of all, so Z belongs to that, if Z belongs to T01 of X, and the real and imaginary parts of this vector field are both tangent to Y. So we call this the CR structure induced on Y by the complex structure on X. Okay, so if the surface is given by an equation, rho equals 0, then these vector fields that are in this subbundle are the ones that satisfy this equation. D bar rho evaluated on the vector field is 0. Okay, now, there's also an intrinsic way to describe this structure, which I won't go into right now. And it's basically formally integrable, almost complex structure on a hyperplane subbundle. So I pick an even dimensional, codimension 1 subbundle of the tangent bundle, and I can put a complex structure on the fibers of it, and then I make some kind of hypothesis about the integrability of sections of that bundle. So I won't go into the details of that. Okay, so the CR structure defines a differential operator, just like d bar. We call it d bar b. So b here stands for boundary, and it's just the same definition. Now here's this interesting fact. Suppose f is a holomorphic function. So we have our complex manifold. We have a hypersurface.
Can you change the label?
Oh, I see. You can't turn it over. You can see. Okay, so we're. You have a hypersurface. And I have a holomorphic function, which maybe is just defined on one side, but let's say smooth up to the boundary here, or C1 up to the boundary. So here, it satisfies the equation d bar f equals 0. It turns out that if I restrict it to the boundary, well, this is a system of equations. It's just differentiating along certain complex directions. If I look at the directions that are tangent to the boundary, well, that's just d bar bf. That must also be 0. And in fact, that equation, the d bar bf equal to 0 equation, only actually requires the restriction of f to the boundary to actually evaluate that condition. So we have this interesting situation where holomorphic functions defined on one side of the hypersurface satisfy an equation on the boundary, and it turns out that under appropriate convexity conditions, which we'll talk about a little later on, any solution to that equation on the boundary actually extends to define a holomorphic function in the ambient space, at least on one side. So again, that's something that is totally different from what happens in one dimension, one complex dimension. There's nothing like that. So this is a huge difference between one and several variables. Okay, so the bundle T01, along with its conjugate T10, they span a complexified hyperplane bundle, and we let theta be a one form which defines that bundle, so its null space is H, and we choose a vector field T which is transverse to H, so we normalize it so that theta of T is 1. Now, another structure that we can define on a CR manifold is a quadratic form. It's called the Levy form. And what you do is you take the bracket of a 0, 1 vector field with a 1, 0 vector field, and what you do is look to see, does it have any component in the transverse direction modulo H tensor C, modulo the sum of the two pieces. And the coefficient of that is what's called the Levy form. Okay, so it's actually not canonically defined. If I can change T to another transverse vector field, but it will just change L by sort of a conformal factor. And what we're interested in really is the positivity of that quadratic form, which doesn't really have anything to do with the choice of T. So we say that the manifold is strictly pseudo-convex if this this quadratic form is positive definite at every point. And in the case that y is a hypersurface defined by rho, we can express theta and d theta in terms of the defining function. Okay, so strict pseudo-convexity is a very natural condition in complex analysis. It's a condition which is invariant under holomorphic maps. And it's equivalent to the following statement. If y is a hypersurface sitting in an ambient complex manifold X, then it's strictly pseudo-convex if and only if analytic varieties make contact at most 1 with y. So it actually measures the order of contact between analytic subspaces of X and this hypersurface y. Okay, so in the case that y is the boundary of a manifold, where we choose our defining function, and we always normalize the defining function to be negative on the interior manifold, then we, as noted above, we can let theta be given by id bar rho. And why is id bar rho a real one form? Well, because d rho is 0, and d rho is d bar rho plus d rho. That's confusing, huh? Some of the rows are Roman, some of the rows are. So d rho is d bar rho plus d rho. If you add that to the tangent space, it's 0, because rho is constant on y. And so what this means is that the imaginary part defines a real one form, which is non-vanishing. Okay, now, here's an important thing to observe here. The CR structure is strictly pseudo-convex if dd bar rho is positive definite. And notice that this depended upon rho being negative on the inside. So the CR structure knows which side of the hypersurface the manifold lies on. Okay, so for example, the ball, the sphere is the strictly pseudo-convex boundary of the ball, but if I think of it as the boundary of the exterior of the ball, that's what we call strictly pseudo-concave. Because when we change the sign of everything, the Levy form will become negative definite. So the CR structure knows which side of the manifold it lies on. That's an important fact about that we'll keep in mind. Okay, so here's an example. Let y be the unit sphere, so the defining function is just this simple expression. It's negative inside the ball. The CR structure is actually spanned globally by one vector, z bar. The transverse vector is given by that. It's the imaginary part of the radial vector, z bar dz bar plus w bar dw bar. The contact form is given by that, and the Levy form is given by the imaginary part of the Kähler form. So the boundary of the ball is strictly pseudo-convex as the boundary of the unit ball, but it's strictly pseudo-concave as the boundary of the complement of the unit ball. Okay, so what I want to talk about today are CR structures on compact three-dimensional manifolds. And what I want to talk about has to do with the deformations of this structure. So this is actually a subject which is very, very similar in some ways to tight field theory, because these things are like the odd-dimensional analogs of Riemann surfaces. And the deformations are really quite similar to deformations of Riemann surfaces, which can be described by Beltrami differentials. So the deformations of the CR structure are almost the same thing. They're basically the sections of a line bundle. Okay, so this is how we describe them. So in 3 dimensions, if y has 3 real dimensions, then this 0, 1 bundle is a line bundle. Just like on the sphere, it's spanned by a single vector field locally. So the integrability condition is vacuous. Right? If you just have one section, its bracket with itself is always 0, or its bracket with a multiple of itself is a multiple of itself. It's vacuously integrable. So this means you can describe the deformations very, very simply. It's just a question of looking at homomorphisms from the 0, 1 bundle to the 1, 0 bundle. And then the deformed CR structure is just given as the graph over the reference CR structure, according to this prescription here. And this, if you know the theory of Beltrami differentials, is exactly how you describe the deformation of a conformal structure in terms of the Beltrami differential. It's the same formula, in effect. Okay, now, the contact group. So we're going to assume here that this hyperplane field, which in the case of a 3-dimensional manifold is actually just a plane field, actually defines a contact structure. And this is actually a consequence of strict pseudo-convexity. In fact, in the 3-dimensional case, it's equivalent to strict pseudo-convexity. So we're going to look at this. We're always now, from now on, be considering Y is a 3-dimensional manifold and H is a fixed contact structure on Y. The group of contact transformations acts on the space of deformations of the CR structure. Now here's where there's a difference between the deformation theory of CR manifolds and tight field. Tight field spaces for compact Riemann surfaces are finite dimensional. Even for a compact 3 manifold, the deformations of the CR structures is always infinite dimensional. Even if you mod out by the action of the contact group, it remains infinite dimensional. And the reason for this is that there is a Riemannian geometry, it's not a Riemannian geometry, it's a Cartan geometry. There's a Cartan connection defined on a principal bundle canonically by the CR structure, which means that the CR structure actually has local invariance. It has a curvature tensor, which is a local invariant. And if 2 CR structures are locally equivalent, then when you pull back the bundle and you pull back the connection, you pull back the curvature tensor. So you have local invariance. And that tells you, in effect, that the parameter space which describes these structures is going to be infinite dimensional. Now, one way to change the CR structure on a hypersurface is just by wiggling it. So if I take the sphere, in arch in C2, and I just wiggle the embedding a little bit, well, that's way more than I want to, I wiggle it and keep it pseudo-convex, that's typically a different CR structure. It's inequivalent to the CR structure I started with. And so there's this infinite dimensional space of wiggles which produce inequivalent CR structures. Now, in some sense, that's a trivial deformation. But nonetheless, it produces a different CR structure. Okay, so this theorem actually, this is a theorem that goes back all the way to Poincaré. This is one of the first things that they realized was really different about several complex variables, was that the Riemann mapping theorem was just plain and simple false. There was no generalization of it in any obvious sense. Okay, now, you might ask, well, what is there to study here? I mean, I just have a space of sections of the vector bundle. Well, I can talk about maybe constructing a transverse slice to the group action. I'm not going to mention any of that. I'm actually interested in a geometric problem. And this geometric problem appeared very, very early in the subject. So people started to look at deformations of the CR structure. And let's just take the case of the three-sphere, because it was actually this case that was sort of crucial for the field. And you take the simplest imaginable deformation. I'm just going to take a constant multiple of the z vector. I'm going to change my vector from z bar to z bar plus epsilon times z. So that's certainly the most innocuous imaginable perturbation of the structure that you could ever write down. It defines a different CR structure. It has a very, very strange property, very kind of unexpected property. So if epsilon is not 0, the solutions to the equation z bar epsilon f equal to 0 are all even functions. Now, when epsilon is equal to 0, the solutions to that equation include the restrictions of all complex polynomials to the boundary. So all functions of the form z to the j, w to the k minus j, if you just restrict one of those polynomials to the boundary, that's the solution of the equation when epsilon is 0 for any k and j, where k, j has to be less than or equal to k. What happens when epsilon equals 0 is that whenever k is an odd function, it kind of disappears as a solution to the equation. More precisely, it doesn't really perturb. If k is an even number, then I can perturb this function and get a solution of that equation, z bar epsilon equals 0, very close to this. But if k is odd, I can't. So something really very, very strange happens when I perturb the structure. So it's a very innocuous deformation, but an infinite dimensional subspace of the kernel just disappears. So the question is, where did this go? Where did the kernel go? Okay, so there's a couple other bad things I can say about this, and this is sort of why this problem is interesting. It turns out that not only did all these functions disappear from the kernel of the operator, I can no longer find a complex manifold with boundaries so that this three-sphere with this CR structure on it is the CR structure induced on the boundary. So I started out with this CR structure, which was induced by having this thing be the boundary of the ball. I changed the vector field a little bit, and suddenly there's no complex manifold for which this is the induced CR structure on the boundary. So these two kinds, this analytic and geometric pathology, kind of seem to be connected to one another. So we want to understand first of all, what happened to the eigen, what happened to the null space. So to do that, we introduce a Laplace operator. In this case, this is the Cohn-Rossi d box B operator. And it's just the same formula as everyone's used to for, let's say, the Hodge Laplacian, but the operators now are just the d bar B operator instead of the exterior differential. So this operator is self-adjoint, and it's almost got a compact resolvent, but for the fact that it has an infinite dimensional null space. So the box B operator has an infinite dimensional eigenvalue at 0 because every boundary value of a holomorphic function is in the null space, and that's an infinite dimensional space. But other than that, it has a perfectly nice spectrum that runs off in a uniform way, nice measured way to infinity. So what happens? What happens when I turn epsilon on a little bit and I change the structure? What happens is the spectrum changes. And here's sort of one of the horrors of complex analysis, that this actually happens. What happens is I have this infinite dimensional eigenspace at 0. And when epsilon is not 0, what happens is I get an infinite sequence of small eigenvalues that converge to 0. And they converge to 0 extremely fast. So it's something like estimated as something like e to the minus j over epsilon, absolute value of epsilon. So they're very, very hard to see. For any kind of analytic technique will tell you that those numbers may as well be treated as 0. But they're not 0, and there's an infinite sequence of them. And what's happened is that's where the odd CR functions went. They turned into eigenfunctions for these small eigenvalues. Now, the other part of the spectrum behaves very nicely. It just deforms continuously under epsilon. And in fact, the truth of the matter is all of the spectrum is deforming continuously under epsilon. This is just what happens when you continuously deform an infinite dimensional eigenspace. You get this very, very complicated sequence of non-zero eigenvectors. Okay, so the odd CR functions have turned into eigenfunctions for the small eigenvalues. And what we should think about is that these small eigenvalues, this infinite sequence of numbers, is basically the obstruction to filling this manifold. So, and we'll see that there's a sense in which that's really correct. Okay, so this is what we do. This is what we do. We have our reference CR manifold, and we always assume that reference CR manifold comes as the boundary of a nice complex surface. So there's always some CR structure on this contact manifold which can be filled in. We call this the reference structure. And then what we say is we're going to define the subset E of Y and H. These are the fillable structures in this basic deformations of the CR structure. And we want to understand what kind of set this is. We call them fillable deformations. And these are the deformations that you feel like they're the sort of geometrically reasonable deformations. These have something to do with complex geometry. And the other ones, there's some kind of weird pathology. Okay, so the fillable structures can be wiggled, and they're always fillable structures, right? Because I just wiggle the thing in the ambient space, it's still bound something. It's still fillable. So that means that the fillable structures, the set E, is always infinite dimensional. Now, the unfortunate fact is it's also infinite codimensional. Now, we already suspected that because we had an infinite sequence of eigenvalues that were obstructions to fillability. So that's an infinite number of parameters. Now, it's not obvious that those are really independent parameters in any serious sense of the word, but we get a bad feeling about having an infinite number of things that are keeping something from happening. And in fact, you can prove without too much difficulty that in fact E is both infinite dimensional and infinite codimensional. So it's a very unprepossessing situation to do analysis in. So there turn out to be a sequence of properties that are equivalent to fillability. So this fillability is sort of this geometric property. There's another geometric description, which is that the algebra of CR functions, that's the null space of the D bar B operator, is sufficiently rich to embed the manifold in Cn for some n. So that is, I can find some collection of CR functions on my space Y, such that if I just look at the image of Y under that collection of functions, it's a submanifold of Cn. And Harvey and Lawson proved that under such a circumstance, that submanifold is actually the boundary of a complex analytic space, and so then you filled it in. This is what's called the complex plateau problem. Now here's an analytic property, which is equivalent to these geometric properties. The analytic property is that the range of the D bar B operator should be closed as an unbounded operator on L2. Now, I won't describe that further, because it's equivalent to the statement that the range of the box B operator should be closed as an unbounded self-adjoint operator on L2. And that's much easier to describe when that happens and when that doesn't happen. It's basically a theorem of Banach. That happens if and only if 0 is an isolated point in the spectrum. So it's exactly this appearance of the small eigenvalues converging to 0, making 0 a non-isolated point in the spectrum, that makes the thing non-fillable. Okay, so when you're in such a parlous state, you have to set your sights fairly low. You don't want to ask any very hard questions, so you would like to ask some fairly simple questions. So the first question you'd like to ask is the subset of fillable structures closed, let's say in the C infinity topology, as a subset of the space of all deformations? Now, that's actually not an easy question because it's infinite codimension and infinite dimensional. So it could very easily not be closed. So let's suppose you could answer that question. You might want to know if it's locally path connected. So can you deform through infillable deformations back, let's say, to this reference deformation? That's a fairly reasonable question. Now, if you were very, very ambitious, you might try to prove the following theorem. You might try to prove that the fillable deformations are actually a fibration. And they're a fibration over a finite dimensional analytic base. And you might even want to say that the fibers are obtained just by wiggling the boundary within some ambient complex space. And what would the base be? Well, the reason that you might suspect this is that suppose your space is, you start out with an isolated singularity, surface singularity. So you have something that looks like a cone, and then you have a boundary in it. And from the picture, you can see two obvious ways to deform the CR. One way is just wiggles, move the hypersurface in the ambient space. The other thing you might do is you might try to deform the singular space. It's just a well-known fact in algebraic geometry that singularities tend to have a finite dimensional space of deformations, which are also analytic spaces, but they're analytically inequivalent. And so one would expect that if you did that, you could sort of follow this hypersurface in the deformed space, you would get more deformations of the CR structure. And that, in fact, is true, and that's why you might think that this last statement here is true. That you might say, this is the only thing that I can really do. I can deform interior singularities or wiggle a hypersurface in an ambient space. That's really the only way I can get these CR structures. Okay, that's an ambitious question. Okay, today I'm going to answer just the first question, because I can actually answer the first question. The other questions I can answer in certain special cases, but there's actually no general theory at all. Okay, so this last property that we had before shows that the infinite sequence of eigenvalues are the obstructions to embeddability. So this suggests that maybe what I should try to do is I should try to count them. Maybe I can count the small eigenvalues. Now, what does that mean? Well, we fix a reference structure, which is embeddable, and it has its own self-adjoint Box-B operator. And what I mean is this. I have a certain spectrum with a reference structure, and an eigenvalue is small if it's small relative to the eigenvalue, this first eigenvalue. So when I perturb the structure, I understand what I mean by a small eigenvalue of a small perturbation. It's an eigenvalue which is close to 0 and smaller than lambda 1. So this is what I mean by small eigenvalue. Now, the problem here is that a priori, there could be deformations for which there are a finite number of small eigenvalues. And when you think about that, what that means is that if you just make a little tiny deformation and you get a finite number of small eigenvalues, they're going to be very small. So if I were to try to use that structure as my reference structure, well, that would be a completely different notion of what I meant by a small eigenvalue. Right? So if I were to, I have my reference spectrum like this, and I deform the structure a tiny little bit, and I get a couple of small eigenvalues down here. Well, now that's what's meant by a small eigenvalue with respect to that reference structure. So the concept of small eigenvalue is a little bit slippery. So if you fix the reference structure, you can be precise about what you mean. But if you allow the reference structure to deform, the concept is meaningless. So you have to be careful. So this is what you have to do. There's a standard trick for comparing infinite dimensional spaces. So here I would like to compare the null spaces of two D bar B operators, which are generally speaking frequently going to be infinite dimensional spaces. In the case I'm interested in them, they're both infinite dimensional spaces. So I introduce a little notation here. When phi is a deformation, I will often sort of label things connected to the deformation with some label like that. A superscript, frequently appearing before the operator. That refers to the D bar B operator defined by the deformed structure. Now, whether or not the structure is embeddable, the null space of a differential operator like that is always a closed subspace. Now, it could happen that that closed subspace is one-dimensional, consisting entirely of constant functions. But it's always a closed subspace. And in most cases, it's infinite dimensional, but could be one-dimensional. But in any case, since it's a closed subspace, it's always sensible to talk about the orthogonal projection onto that subspace. And so I use this notation to denote the orthogonal projection onto the null space of that differential operator, and we call this the sigma projector. So I picked some measure to make sense of the notion of orthogonality. So far I haven't said anything about measures. So you need to have some measure to really define what you mean by orthogonal projection in L2. So we just picked some measure. It won't matter. Okay, so several years ago I proved the following theorem. So I proved this theorem that said that if I start out with this three-dimensional compact manifold, and I start out with a reference CR structure which is embeddable, and I let S1 be the signal projector for some deformation of the CR structure, I look at this restriction. I look at S1 as a map from the image of S0 onto the image of S1. So I restrict the projection to the null space of my reference structure. And the theorem is that the structure which defines S1 is embeddable if and only if this is a Fredholm operator. So that means if and only if it has a closed range and a finite dimensional kernel encoder. Okay, now it could happen. The worst thing that can actually happen is that it has an infinite dimensional null space. So it's always a semi-Fredholm operator. And I let R index, S0, S1, denote the index of that operator. So that's infinity if it happens to be a non-fillable deformation, and it's finite if and only if the deformation is fillable. Okay, so a lot of choices are actually made to define this. I have to represent the operators, I have to pick an orthogonal projection, there's an action of the contact group, there are all kinds of things that are fixed in order to define this number. It turns out the number doesn't depend upon any of those things. It's a really genuine geometric invariant. And it's a cosine. So that is, it's skew symmetric in the two projectors. If I interchange which I mean is the reference projector structure and which I mean is the deformed structure, it just changes the sign of the difference. Yes?
So that means that Analytic Property is one of the first and
No.
because this is
No, it has nothing to do with smallness. We'll get to that. Yeah, that's exactly what doesn't happen. And it satisfies this cosine. So if I have three projectors, I get this nice formula. Okay, now, as far as small deformations go, well, if I fix a reference structure, then I understand what I mean by a small eigenvalue, and I understand what I mean by a small deformation. And the theorem, it says that the relative index of a small deformation is actually non-negative. It actually equals the number of small eigenvalues. So this invariant actually does count the number of small eigenvalues for small deformations. However, and this is very important, it's defined globally. There's no smallness hypothesis anywhere. It's defined for any deformation. And that's very, very important. Well, it's the way I define it. It's a map from T01 to T10 with supernorm less than 1. So it's a ball in the end. Okay, now, those are the good things I can say about it. There are also a lot of bad things to say about it. So people who work in Fredholm theory see Fredholm operators and think, oh, this is great. Fredholm operators have all kinds of marvelous properties, all kinds of stability properties, their indices are computable. This is a great class of operators. Now, let me just say why these Fredholm operators do not have those properties. When people talk about Fredholm theory, they're usually talking about a map between two fixed spaces. And it's true that if you have Fredholm operators between two fixed spaces, they have all kinds of marvelous properties. The problem here is that I don't fix the target space. The target space varies. It's the image of the second projector. So I don't have two fixed spaces. And that means that many of the ordinary properties that we're used to, well, the good properties of Fredholm operators, they kind of go away. So that's another fact, and this is sort of not unusual in this kind of thing. The index is not symbolically defined. That is, I can have two projectors that differ by a smooth projector. Their indices are completely different. I mean, they can be as large different as you want. So it's not symbolically defined, and it's, of course, highly unstable under perturbations. Okay, so those are the bad things that we can say about it. But those are intrinsic to the problem. Okay. But nonetheless, what we found is a sort of global way to count something like small eigenvalues. And this is where it becomes extremely useful. So it defines a stratification of the set of embeddable structures. So for any embeddable deformation, the relative index is finite. So I say, let's look at the following sets. For each non-negative integer, I look at the deformations where the relative index is smaller than or equal to n. And then I have to shrink it a little bit. So what I do is I pick a positive delta, and then I take that stratum, and I intersect it with deformations whose norm squared is less than a half minus delta. Okay, that's a big ball. It's not the whole space, but it's a big ball. And the important thing about that ball is it doesn't depend upon the reference structure at all. It's a fixed size ball. And this is important because we have the following theorem. If you fix an integer n and a positive number delta, these sets are closed in the C infinity topology. So what it means is, if I have a sequence of structures that are all in this stratum, and they converge in the C infinity topology to something, well, the limiting structure is automatically fillable, and it belongs to this stratum. So I've kind of reduced the problem somewhat to sort of some kind of finiteness thing, something fairly concrete. So I see exactly what the problem is. The problem is that I have to try to bound this relative index. Okay, so two things are notable about that result. First thing is notable is that only an upper bound is required. I don't have a lower bound. I just assume that the relative index is bounded from above. And the other thing is, as I said before, that the smallness hypothesis, that the norm of the deformation has to be less than a square root of half minus delta, doesn't have anything to do with the reference structure. Okay, now how I prove this? Well, I have to try to recover some of the properties of familiar Fredholm operators. And the way this is done is that there is an operator, sort of canonically defined operator, that you can write down, which is always a Fredholm operator. It doesn't matter if the structure is embeddable or not. Has a map from L2 to L2. And it has this amazing property that if I restrict this operator to the kernel of the deformed structure, it gives me the single projector of the reference structure restricted to the kernel of the deformed structure. So what I'm doing here is I'm interchanging the roles of reference structure and deformed structure. And I have this nice fact, and that's what allows me to prove that theorem. And notice that because of the cocycle, the skew symmetry, this relative index, which is sort of the one I'm interested in, is minus that one. Okay? Okay, so how much time did I start? 4:20?
You have 7 minutes.
7 minutes. So I want to prove that this thing is closed. So it suffices to show that there's...
No, I'm sorry, I deprived.
Not yet.
No, 7.
Now it's 6.
Make it 5. Okay, so what if I could show that the relative index is either bounded by some fixed number or it's infinite? Is that a wild conjecture? Well, maybe it is, but there were some examples when I made this conjecture that showed that it could be true. Laszlo Lemper had proved this beautiful stability theorem. And the theorem said that if you had a strictly pseudo-convex hypersurface in C2, and you had a deformation of the CR structure, which was a small deformation, but it was fillable, then the only way that that could arise was by wiggling the hypersurface in C2. Okay, so this indicated that the relative index conjecture is actually true with n equal to 0. That either, for a small deformation at least, either the relative index is 0 or it's infinite.
I thought you just took the CF with those small durations of sphere.
They are, but they're not fillable. The hypothesis is that it has to be fillable. They are perturbations.
It's not equal to 0. So.
Yes, but epsilon not 0, it's not full. So the relative index is infinite. So what he's doing is he's taking a hypersurface in C2. He's saying, let's do an abstract deformation of the CR structure, but assume that it's fillable. Then what he showed was the only way you get those is by wiggling the embedded. And then necessarily, the relative index is 0. Okay, and I knew this other theorem. This is the theorem of Ailey-Oshberg. And what Ailey-Oshberg showed was that in the case that y is S3, then in fact, this conjecture is true globally. Any embeddable deformation of the CR structure of S3 actually arises as the boundary of a standard 4-ball, and it can be deformed along a path, strictly pseudo-convex hypersurfaces, to the round ball. And again, using properties that I had established for the relative index, I could show therefore that the relative index was always 0 in that case. So it wasn't completely crazy. Sometimes it was true. Okay, now I'm going to talk about why this is always true. And somehow or the other, it seems to me this slide is out of order. I'll just mention it. This is an important fact to keep in mind. If X is the boundary, it's a strictly pseudo-convex complex surface. So it's a smooth, complex manifold with a strictly pseudo-convex boundary. They always have the homotopy type of the two complex. And this is because you have the strictly, you can blow the space down, you get isolated singular points, and on the complement of those isolated singular points, you have a strictly Clarice harmonic exhaustion function. Such a function only has critical points of index 0, 1, or 2. In fact, you can deform the complex structure a little bit, make all of the singularities go away without changing the topology of the resolved space, of the blown-up space. And so you have this beautiful pattern. There are always two complexes. And this is a very crucial observation. Okay, so we need some way to estimate the relative index. It's unstable invariant, so we feel like, well, maybe you can't do it. So I had a conversation with Laszlo about it. He said, maybe you could just write down a formula. And, he had some suggestions, and I put it out of my mind for a while. And maybe 5 years later, I decided, I'm going to try to do it. And sure enough, turns out that you can. So we start out again in our usual situation. We have a three-dimensional contact manifold. We have two cyclic projectors that correspond to fillable structures. We let x0 and x1 be the complex manifolds that they bound, and they're the minimal resolutions of the unique normal Stein spaces, whatever that means. And here's the formula. So we have the following formula. The relative index is the difference of the dimensions of the H01 groups. So this is a sort of analytic contribution to the relative index. And then there's a topological form, part of it. So it's the sum of the signature plus the Euler characteristic of the one space minus the signature plus the Euler characteristic of the other space. Okay, so I don't know, I wrote that formula down in 2005. And it took me a long time before I really looked at that formula. Well, I did eventually look at it, and so what are the bits and pieces? Well, the chi is the topological Euler characteristic. The signature is the signature of the cup product pairing on a slightly weird space. It's the image of the relative cohomology in the absolute cohomology. Okay, this is something in topology very, very common, especially in the theory of four manifolds. And so we introduce a number. V2 plus and minus are the dimensions of the positive and the negative space on which the signature, the cup product pairing is positive or negative. And V20 is the dimension of the null space of that mapping from the relative to the absolute cohomology. And of course, the second Betty number is the sum of those numbers. Now, that's not totally obvious. You have to use a bunch of duality theorems, but it's not a hard fact. Then you have the following formula. And for some reason, I didn't write down this formula until, I don't know, 3 months ago. It just took me a long time to realize I should look at the formula. So we look at this formula. So x0 is our reference. So this is some number. We don't care what it is. It's a number. And, well, this could be nasty. This could be one of x1. This really depends upon x1. But notice, all this other stuff, these are negative numbers. They're non-positive numbers. All I need is an upper bound. So frankly, I don't care about them. Now, it turns out the B1 is actually also controlled, because the B1 of the interior is bounded by the B1 of the boundary. This just follows from the fact, again, that the interior is a two complex, and the long exact sequence of the pair, manifold and its boundary. And so, I get the following estimate. This is an estimate, upper bound for the relative index. Bounded by the dimension of that space plus these topological numbers. Well, they're numbers. So, it proves the relative index conjecture in basically full generality. Okay. So, it leads very easily to the statement that the set of CR structures that are fillable is closed in the C infinity topology. You have to be a little bit careful, remember, because there's this issue that I can only look at balls of big radius, essentially, square root of half. Well, you do the following little trick. I have a sequence converging. I have a sequence of structures that are fillable, and they're converging into some structure. I want to show that structure is fillable. Well, what I do is I just move my base point so that it's within a half of the limiting structure, right? A quarter of the limiting structure, whatever. I can make it as close as I want. So I can always reduce myself to that situation, and then I have the closed cycle formula that tells me that nothing serious really happens to the index. I just add a constant to it. So the relative index only changes by a constant. In fact, it doesn't really make any difference, because I can just compute all the relative indices relative to my new choice of base point, and I have my theorem for that choice of base point too. So I still have the upper bound. So the conclusion then is that the whole thing is taking place within a ball of radius square root of a half, and so I can apply that theorem. Okay, now I don't know if the relative index is bounded from below, and there's a conjecture of two contact topologists, Oshbagy and Stipschitz, that says that among Stein fillings of a contact 3 manifold, the second Betty number should be globally bounded. Okay, I don't know if that's true. However, an interesting consequence of the formula up here, of this formula, is that among sufficiently small deformations it must be true. And that's because I know that for sufficiently small deformations, the relative index is always non-negative. So that means these guys here, this guy's here, can't get to be too big. So we prove sort of a germ version of their conjecture. Now it's a germ version because the size of the neighborhood depends upon the reference structure. Right? Because it has to do with the notion of a small deformation, and as we know, the notion of small deformation depends critically on the reference structure. Okay, now, this is not a trivial conjecture, and the reason is that it's known that there are examples of three-dimensional contact manifolds with infinitely many topologically distinct Stein fillings. So that's a kind of unpleasant fact. Okay. I think this is probably a good the next part of the talk I was going to discuss how you prove the relative index theorem. Well, it's very complicated. And it requires a development in kind of a particular direction to what I've been talking about thus far. I have to talk about boundary value problems for spin-C Dirac operators. I think it would be a bad thing to start this late hour of the day. So I'll just stop.
Any questions?
Yes.
Is there a higher dimensional possibility?
Well, the interesting thing about the subject is the question does not arise in higher dimensions. In higher dimensions, there's an integrability condition. And this, first of all, dramatically reduces the number of deformations. And then also so we have this D bar B complex. So you have, in dimension 3, you only have 2 degrees. You have 1 and 0. And what happens is they're basically the same. And neither of them are well behaved. In dimension 5 and above, you have 0, 1, 2, so on and so forth. It turns out that as soon as the dimension is at least 5, the operator in degree 1 is always subelliptic. So it always has finite dimensional null space. And the point is, just the usual trick, you can intertwine 0 and 1 off of the null space. So that shows you that the spectrum at 0 cannot have any points of accumulation. Because the spectrum at degree 0 is the same as the spectrum at degree 1, other than what happens exactly at 0. And so the problem actually disappears in dimensions bigger than dimension bigger than 3. So it's an exclusively three-dimensional problem. Yeah.
So the number of small eigenvalues that were peeled off, the number that were split, that's supposed to be sort of the dimension of this analytic base that sort of measures.
That would be a nice idea. No one has any idea as far as I know. The only case where I can actually prove that statement in one case. So for the case of maybe the line bundles over P1. So I take line bundles over P1, I look at hypersurfaces in these line bundles, and I can prove, in fact, that the space of the small deformation is, in fact, exactly as I described it. It's infinite dimensional fiber bundle over the deformations of that singularity. Otherwise, who knows? A very interesting question might be, what is the zero stratum? What is the space of deformations for which the relative index is 0? Now, if the reference structure is a Stein manifold, then they're all wiggles. Nothing else can happen. So here are two interesting questions. So, okay, so then, but if it's a singular space, I don't know. Can they all be described as fibers in a fiber line like that? That's a pretty reasonable thing to think might be true, but I don't know how to prove it. There's another question. If the reference structure is a Stein manifold, is it possible for the relative index to be other than 0? Is it possible to somehow deform it so that the thing that fills in is quite different? Different, topologically different. You can't really, the H01 can't do anything because H01 if the reference space is 0. It's not going to, it can't become negative. Well, unless something complicated happened topologically. So something complicated could happen topologically, get a singular space. I don't know. It's a very good question. So it's a reasonable thing to conjecture that any sufficiently small deformation of a structure that bounds a Stein manifold will also bound a Stein manifold and will therefore just be a wiggle. But I don't know if it's true.